We have seen stochastic optimization. A small variant of it is if we take the worst case instead of the average case cost. And this has a name called robust optimization. The terminology here is very shaky and not very helpful. So there are robust constraints that are called chance constraints in the case of stochastic optimization. And there's not much difference here. Finding the expected cost is sometimes very complicated. So using distributions, we have seen an example with the Gaussian distribution that was fairly tractable, although it led to quadratic terms that may be a bit difficult to use. Very often, what we do instead of minimizing the expected cost is we minimize the worst case cost. Not so much because it makes sense, but because it is more tractable here. The worst case cost is what is expressed here. I have the same framework as I said before, except that I don't know a distribution of the disturbance, but I know bounds. I know the disturbance lives within some constraints, which, as we have seen in practice, is more or less the same, because if we have a distribution, we will with high probability lead to that. But as we will see, and you will see in particular in the lab, you can appreciate, it is a bit easier to consider as cost the worst case cost. So the problem is always the cost depends on the disturbance. We need to get rid of the disturbance in the cost. So one way is to take the expectation, but if the cost is nonlinear, that may be tricky. So another way is to take the worst case. This corresponds also to a case where what you think you will pay very much is if the cost becomes very high. So you want to be protected against very high costs. Whether this is good or bad is a more philosophical question, but this is what it corresponds to. Let's do it again for our grid example. Our costs, our instantaneous cost is given here. And then if we apply this, we have to take the max. Now I wrote it in all detail. Usually we don't do it in such a lengthy form. Here, it's the max over all the disturbance, which is exactly what it means here. Subject to the constraints, which again have the disturbance here. Note that the disturbance appears 2 times and not necessarily with the same value. Here we say the thing I minimize is the cost that could occur in the worst case. So it will occur for some value of the disturbance, which I don't know, and for the value that will produce the worst cost. In addition, I assume that every constraint must be true for also all values of the disturbance. In particular, it will be true for the worst value of the disturbance. But for every constraint, there is one worst value of the disturbance, which is not necessarily the same here. So that's the price to pay for robustness. We want to be robust. That means we don't know exactly what happened, and then we are covering ourselves against a number of cases. But in particular, there will be a cost, a hidden cost to that. So this is what we obtain in this example. How do we solve it? The robust constraint we've seen, how to solve it. Now, how do we get rid of the cost here? Well, in this specific case, we can do it manually. We can compute the worst case cost. The worst case cost was given by this here. It's a linear function of L1, L2, L3 here. And if C1 is positive, it's linear times the sum of the two. So this is an increasing function of each of the variables. The variables have independent constraints. Independent here means that the set that defines the possible values of the constraints are Cartesian products. So the range of L1 is independent of the value of L2 and L3. If L2 has a specific value, L1 can still take any value in this range here. That's what independence means here. So in such a case, it's very simple to find the maximum. The maximum is obtained when each of the disturbance takes the maximum value, 1.1, 1.1, and 5.2. So we will think we will pay for the cost that will be worst when the loads are maximum, which is intuitive here. So I can factor that into the expression, and then I have exactly this to solve. So if we compare to what we had before, when we took the average cost, which we took when the cost was linear. Here we had, if C1, C2, C3 are simple linear functions, it's only the constant here that has changed. In particular, the optimal point will be the same if the costs are linear. So in that case, that will not change anything. In the stochastic optimization, when the costs were linear, we replaced 7.4 by 7, which was the average. In general, however, things will not be as simple. Usually the disturbance will not be easy by inspection to find what is the worst case disturbance for the cost. So we will need to solve an optimization problem that has the max in the objective function here. So we'll have to minimize over U the max over the disturbance of the costs of U and the disturbance. Here I put a D prime. Why did I put a D prime? Well, there's no good reason. I could put D here, but this is just to emphasize that this is a dummy variable. Dummy variable means whatever name you give to it doesn't change anything. It's like when you have an integral. If you have to compute the integral f of x dx, if you call y instead of x, f of y dy will give the same thing here. So here, this is to emphasize this. But it's a fantasy, of course. In reality, you don't need to do it. How do we solve an optimization problem where there is a max in the objective function? Well, we've seen that last week. We've seen that if there is a max in the objective function, last week, to be honest, we saw it when the objective function contains terms that were the max of a finite number of constituents. Here it's an infinite number, but it doesn't matter. The rule is exactly the same. If I want to minimize something that contains a max, for every max, I can introduce one additional optimization variable. Here I call it epsilon. And I add the constraint that epsilon must be larger than all of those things here. I could have called it D prime or D, doesn't matter, it's the same. So here I have removed this max. That's the max removal operation we've seen last week, but at the expense of adding one optimization variable, epsilon. And then we have one more robust constraint here. Now, the difference with what we saw last week is that D is in a continuous set, so this will not be solved by simply adding constraints and asking MATLAB linprog to solve it. We will need to work a bit more, but we've seen how to do that. At least if phi is linear and U and D, then we can solve it like we saw a minute ago. For example, if I apply this to this problem, I will obtain minimize epsilon, where I've added epsilon as an optimization variable, and I've added this constraint here, and this constraint must be true for every L1, L2, L3. If C1 is linear, that will be easily separable here. Voila, that's the main tricks about this first phase. Quick quiz to verify your understanding. Here I'm proposing two possible implementations of my robust solution problem. Which one is correct? I close the poll in a few seconds. The majority says C, which is the correct answer. Both are correct. In fact, the first one is the one we just saw. I add a supplementary variable, and I add a constraint that will become a robust constraint. This one here. Yes, exactly. This is what I have obtained. I have a robust constraint, then I've removed the quantifier, and I obtain exactly this variable. This one is the one we had seen before when we computed explicitly the max. Of course, the two are the same. The two are correct, therefore the two are the same. They are the same in the sense that they both provide us with a solution of the problem. Technically, they're not exactly the same. Here, I've added a variable, so my problem will be larger. Here, with more work, I could remove a variable. I could work without adding a variable, so my problem will be smaller. That's something quite general. You will be able to exercise that in this and the next lab in particular. De-robustifying constraints or optimization objectives can always be done by adding variables, but there is a price to pay. The more variables there is in your problem, the more difficult numerically it will be to solve it. Voilà. What we have seen so far is that when we have to address uncertainty in the load, in the generation, that naturally leads to optimization problems where there are constraints of the form. For every value of the disturbance, this constraint must be true. And we have seen a simple way to go about it when the constraint is linear in both the control and the disturbance. However, as we will see, there are many cases, and in particular the very interesting cases that are done in practice are a bit more complicated. So we will need to address those, and this is requiring to do an excursion into duality of linear programs. So let's recap a few things about duality of linear programs. If you have done already part 1 of the OPF lab, you should be familiar with duality. So this will look very easy to you. What we are doing now is computing the dual of a linear program. For example, I take this one that we saw already last week, a simple optimization problem, which is linear in its objective with 2 variables and 2 linear constraints plus the constraint that the variables are non-negative. We can cast that to compute the dual. We need first to cast it into the standard form, at least one of the standard forms, and the one I recommend is the one of Boyd and Vandenberg. Casting a program in the standard form can be done in various ways. Here I've done it in one way that is very typical of linear programming, where I specialize the constraints of non-negativity, x and y larger than or equal to 0. I say, for me, this is not a constraint, it's part of the domain of definition. So I call D the set of positive numbers in x and y. Therefore, I have only 2 constraints in this standard model. This is not mandatory. I could have done exactly the same thing by deciding that the set of value of x and y are all real numbers, not necessarily non-negative, and then I would have 4 constraints. Both are possible, and both will, of course, lead to the same or to equivalent problem, but they may lead to problems that have a different formulation. The very classical formulation in linear programs is this one. Linear inequalities and non-negativity that are not treated the same way. So this is what I did here. The benefit of doing that is I have only 2 inequalities, so I have only a small number of Lagrange multipliers. I don't have equalities, so I don't have any new multipliers. I have only lambda multipliers. Here I have 2 inequalities, 2 lambda multipliers. The first step is to construct the Lagrangian, which is equal to the objective function, x plus 2y, plus the linear combination of the constraints. And the constraint must be put in the form a function less than or equal to 0. So that gives us this. So plus lambda 1 times this, plus lambda 2 times that. And remember, in the standard form, we require that lambda 1 and lambda 2 are non-negative as well. That's the Lagrangian. Then we've seen that one way to solve a constraint problem, the saddle point method, consists in solving the unconstrained problem, which is the one obtained when we fix the Lagrange multiplier and we remove the constraints here. So this is what we will do here. The Lagrangian is a linear function. When lambda1 and lambda2 are fixed, this is simply a linear function of x and y, which is what I have pretty printed here. It is equal to ax plus by plus c, where a is this, 1, the coefficient of x here, minus 3 lambda 1, minus 6 lambda 2. So that gives me this form here. So the unconstrained problem is a problem of the form ax plus by plus c, where x and y have to be in the same domain of definition, what I call the domain of definition. In this case, those are the non-negative values of x and y. Now, that's a fairly trivial problem. I have to find the minimum of a linear combination of two variables x and y that are non-negative. Well, if a is equal to minus 1, for example, I will have minus x plus by plus c. I can set y to 0, and minus x can be arbitrarily small, negative. So the inf of this will be minus infinity. So the problem, if a is negative, is unbounded. Remember, when writing the dual problem, we have to restrict the Lagrange multiplier to values such that this unconstrained problem is bounded from below, so that the inf is truly finite here. So here the constraints will be that the coefficients a must be positive or 0, and same for the coefficient b. If either of those is negative, the inf is minus infinity. So we will require that a and b are non-negative. And now if a and b are non-negative, what is the mean? What's the mean of ax plus by plus c? Given that x and y are non-negative, ax plus by is non-negative, so the smallest value is 0. So the inf of this, which is a minimum, is c. So you see here it's very simple. The unconstrained problem has one solution, which is always obtained at x equals 0 and y is 0, and is equal to c here. Therefore, we can construct the dual function. Our goal here is to obtain the dual problem, so we construct the dual function. The dual function is the optimal value of the unconstrained problem when we fix the Lagrange multiplier. So we've seen that the dual function value is equal to the coefficient c. And what is c? C is this here, 5 lambda 1 plus 8 lambda 2. So the value of the dual function is this. And when is it defined? Well, it's defined when a and b are non-negative, which translates into those linear inequalities on lambda 1 and lambda 2. So that's the dual function and its domain of definition. And by definition, we know that the dual problem consists in maximizing the dual, subject, of course, to lambda 1, lambda 2 being in the domain of definition, which gives us this constraint here. Those two constraints come from the domain of definition of the dual function, and those two constraints are from the definition of duality. So this is the dual of that problem here. Now, if you look at it carefully, you will see that it's very funny. It's really remarkable how we can construct it. We see that the objective function, the coefficients of the objective function, 5, 8, are exactly the coefficients that we had in the constraints. And the coefficients that we have in the constraint of the dual, 1, 2, are also the coefficients that we had in the objective function. So the dual, when we go from primal to dual, we exchange the role of the coefficients of the constraints and the coefficients of the inequalities. Similarly, we find that the constraints, which were given by the matrix 3, 4, 6, 7, are here given by the transpose matrix 3, 4, 6, 7, if I read them in transpose mode. So here we also transpose simply the set of the matrix that gives us the set of constraints, and we keep the non-negativity. So this is quite one of the remarkable things. This is what duality with linear programs is extremely convenient. In fact, we can do it once for all. If you look up the Wikipedia representation, you will find this table. There are multiple representations. There are multiple ways to describe a linear program that don't map exactly the Boy and Vandenberg's representation. The one we have seen is this one. I had a min of a linear function subject to inequalities of this form, and we obtain as dual that one. So you can say, but I started from dual, I obtained the primal, when primal and dual are symmetric. So if the dual of the dual is the primal, so you can use the table in either direction here. So this is the row of the table we have used. If you have non-negativity constraints, that's what you obtain. If you have non-negativity constraints and equality only, this is what you obtain. You break a bit the symmetry. So this one is very symmetric. The other ones are not. Here is similarly another form. If I have inequality constraints, but I don't impose that the variable is non-negative, I will have equality constraint here. So it's a bit funny and confusing. Some equality constraints translate into absence of non-negative constraint. Here, inequality constraint translates into the dual variables being non-negative. But to make a long story short, this table is what we care about when we have to construct the dual of a linear program. If we have any linear program, then we can construct its dual automatically using this. One interesting thing is that, of course, we know that strong duality holds almost always. It holds if either of the problem is feasible. Feasible means the set of constraints may have one solution. It's not always the case. We have seen, for example, that when we do a robust optimization problem for our grid and the uncertainty is too large, then the problem becomes unfeasible. In that case, strong duality does not hold, which means the infinite values of the two are the values of the optimal values of the two problems are not the same. But if we can check that the problem is feasible, then we know strong duality holds. So solving one is equivalent to solving the other. The interesting thing for us is that duality transforms a maximization into a minimization and vice versa. So this will be something very useful that we will exploit in a few more minutes. But right now, try your expertise on duality of linear programs and tell me what you think is the dual of this program that is written on the right here. I close the poll in a few seconds. And the majority says B, which is, oops, the correct answer, which you obtain simply by inspection. If you look at the problems, this is a problem that we had seen last week, and this is its optimal value. So the set of x and y is bounded and closed, and the optimal value is of a max is obtained here. The dual problem is a radically different one. So we're in a different space. We're in the space of the lambda mu, or here lambda 1, lambda 2. And the min is obtained for given lambda stars and mu star that are given here. And those values, of course, the lambda mu and xy values are a saddle point of the Lagrangian, as you have seen in the lab here. One thing that is related to what we have seen before, to the complementary slackness, when we find the optimal values of the multiplier, in this case 1/3 and 1/3, we see that they are positive, they are non-zero. And if you remember, the complementary slackness conditions tell us that when this happens, it's mean that at the optimal, the constraints are binding. The constraints are binding. That means the constraint that correspond, those two must be true with equality. If they are not true with equality, that means there's a neighborhood of x to y around which we don't care about the constraints, and then the multiplier would be 0, which is what we can verify here. We find that those two constraints, those two multipliers are positive, which means those two constraints must be true with equality at the optimum, which is exactly what happens here. There is a question on the chat and on the Zoom chat. Should we add the constraint x and y non-negative to the unconstrained problem? So if I look at this problem here and I take those as constraints, the answer is yes. Yes, I can do it. I will obtain 4 Lagrange multiplier. In fact, I will be applying this table here. I will have a minimization problem where I don't have non-negativity constraints here. Of course, I can always construct my matrix B and my vector A that include such constraints. So I can do it. I will obtain a different dual. I will find a dual that has 4 dual variables instead of 2. They will be equivalent. They can be transformed with some work, but they will look different here. So formally, there are multiple ways to obtain a given dual, and in particular, there are multiple ways to use this table here. All of them will lead to different formulations of the problem. This is something important in optimization theory. This is what we've seen also a few minutes ago before the break. We've seen that the same problem, when we try to de-robustify it, we can obtain different formulation, one with epsilon, another one without epsilon. That's exactly the issue. That's why we do in this course those little technical parts to get the best way or the best practice in terms of transformation of the problems such that we obtain tractable problems. But yes, the question to this is, we can do it. I invite you to do it and look at the problem that you will obtain. You will obtain a different problem, and you can also prove that this problem is equivalent, but this will require some work. Voilà. So why did we look at duality? Well, because we will be confronted with problems like before that have a control variable and a disturbance with constraints that involve the disturbance, but now with a term that's linear in the disturbance and the control, but is not globally linear. It's bilinear. Here, this is expressed by saying there is a rectangular matrix B such that we must multiply both D and U by B, D on the left, U on the right. That's arbitrary. I could have put the other way around. It wouldn't matter. Such that the constraints appear in this form here. So the method we applied before doesn't work, because if the method we applied before consisted in separating U, putting U on the left, D on the right, and say, I take the mean of whatever is on the right-hand side. But now if we do that, we'll have U and D on the right-hand side. So the mean will depend on U. So it's not true that we solve an auxiliary optimization problem and we're done. We would need to solve symbolically an optimization problem that has the control variable U. So that's difficult to do. And this is what we will be solving with this method here. For example, assume this toy problem. I need to minimize a linear cost function of U and V over U and V, subject to other constraints and U and V, and subject to constraints that involve a disturbance here. So this has a linear part in U, a linear part in D, and a part that's linear in both U and D, but is jointly bilinear. So this is exactly the form it would take here. So if we want to fit that into this framework, we will see that the matrix capital B here will be, so there is one matrix B per inequality. Here there's only one inequality, so there's only one matrix B, which is in that case a row matrix, 11, 12, because D is single dimensional. If D had 2 dimensions, for example, B would be a square matrix here. Notice here also the constraints on D here required to be put in this form. So here we have two inequalities on D. D is less than 7 and D is larger than 6. So D is larger than 6 means minus D is less than minus 6. So the matrix D that multiplies here will have a -1 because of the second inequality, and the 7 will have this here. So this is how we map this to that. Now the question is, how do we solve such a problem? Well, the method is exactly the same as we saw before, at least at the beginning. So we have to modify the constraints to remove D from it. So first, we will put on the D on one side here, and we will see, well, it has to be true that this function of U is larger than or equal to everything that is on the left, whatever the value of B. So of course, it has to be larger than the worst case, which is the max here. So that leads to an optimization problem, which now, as I mentioned a minute ago, depends on U. So I have to solve for every constraint J, an optimization problem that depends on U, and which is the following one. Find the max over D, subject to all the constraints that D must satisfy of this quantity. Now it's bilinear, but as an optimization problem with respect to D, it is a linear optimization problem here. So there is hope that we can do something smart with it. Let me call P star J of U its optimal value. If I can say something useful about this, then I have removed D from the constraint. The constraint that was here is equivalent to saying that gamma J minus this term here is larger than or equal to P star J of U. So at least in theory, I don't know what P star J of U, we don't usually have a closed form to say how the optimal value on a linear problem depends on the parameters of the linear problem. In general, this is very, very complicated. If there would be such a closed form, we would not solve linear problems using things like interior point methods. We would simply apply the closed form. So there is no closed form, of course, but in theory, this is how we can remove it. So I have recapped here. I have to solve this auxiliary problem, which is now a problem over D here. And now comes the trick. I will use the dual of D. This is a linear problem, so I can easily construct its dual by inspection of the table I gave a minute ago. There is one vector of Lagrange multiplier here, which has the same dimension as the vector C that was the vector of the constraints, and we obtain this form here. We transform a max into a min, and since there was no non-negativity constraints, there is equality here, and the Lagrange multiplier must be non-negative. So this is the problem we obtain. It's a problem that, like the previous one, was parameterized with U, so it depends on U. But now it's a minimization problem, subject to linear constraints here. And if the constraints on the disturbance are feasible, something that we will need to remember to check, we've seen that it may be that they are not feasible, it may be that no control is feasible, but if the constraints on the disturbance are feasible, strong duality holds, so P star of U is also the optimal value of this problem here. And that's the trick we will use. So I'm summarizing what we've done before. I had to compute the optimal value of this maximization problem, which gave us a transformation of the constraint J where there was no disturbance. And I've said also that J is the optimal value of a minimum optimization problem here. Therefore, Pj star of U, which is this min, can be plugged into this constraint. So I have transformed the constraint on U by a constraint which still has an additional variable, which is a Lagrange multiplier, but now it's with min instead of max. Before we had to say U is larger than all, so it has to be larger than max. Now we say it has to be larger than min. What is the difference? Well, the main difference is that being larger than a min instead of a max changes the quantifier. That means there must exist one value of the Lagrange multiplier such that the right-hand side is larger than this. That's the key step. That's the magic of duality. We've transformed something that says U must be larger than all possible values of the blue disturbance D into U must be larger than at least one of the lambdas that satisfy this constraint here. And now I guess you've guessed how it continues. So this is what we have seen here. The constraint on U here is transformed by every constraint that had the quantifier for all D, we replace it by there must exist a vector of Lagrange multiplier. There is one vector per constraint. So J is an index of the vector. Lambda itself is a vector with as many dimensions as C here. But now we have seen that if I have an optimization problem with a quantifier which is there exists, we can solve it by adding these variables, the green one here, as optimization variable. So this is now the same as minimizing phi of U over U, of course, but also over the lambda. The lambda don't appear in the objective function, but they appear in the constraint here. So we have replaced our problem with something that doesn't have any quantifier. So here is in summary what we've done. So that is what we need to do when the constraints are bilinear. If I have an optimization problem with robust constraint where both the disturbance and the constraints appear linearly in joint terms, then I can remove the disturbance and the robust constraints by adding J vectors of optimization variables, so one per constraint. That's the bad news, essentially. The good news is we can solve it, but the bad news is the cost is large. We must add one vector of optimization variable per robust constraint, and the vector has the same dimension as the right-hand side of the constraints of the disturbance here. After adding that, we obtain a problem where all the constraints are linear now. So if the constraints on U are also linear, and if phi is linear, we have a linear program here. That's the magic here. So if we take our toy example that we had before, this problem P0, how many dual variables do we need to add to it if we apply this method here? I close this poll in a few seconds. And the majority says A, but this is wrong. The majority is not always right. The correct answer is B. We need to add one vector of optimization variables per constraint here. Sorry, yes, so how many constraints we have? We have one, but what is the dimension of the vector? Well, the dimension of the vector is the same as C here, the constraint. Now, what are the constraints on D? D, there are two constraints. In fact, D is larger than 6 and less than 7. So we have two constraints on D, which means the dimension of C is 2. So we add one vector of dimension 2, which means we add two optimization variables here. So I need to add two lambda and mu and add those constraints here. So this is how I could transform this problem into a robust one. Voila, time for a break. So we will resume at 11:15. As usual, the break may be also an opportunity to ask questions on the chat, public or private, as you want.